No, it's good.
All right, hopefully everyone online can hear me. I can hear everyone can hear me here. Good morning. We'll get the session started. So the past couple of days, you guys have had the experience of first day walking through basics of mass spec, some introduction to some of the concepts in fair data and all of these processing workflows, quality control. Yesterday, you guys had an intense hands-on pre-processing, an essential aspect to working with any type of mass spec data, especially large types of data. And now we'll kind of move on to the natural next steps today. So this first session, we'll talk about metabolite annotation. It's important to know that you have good quality data. It's important to know that your pre-processing is doing a good job picking your peaks, but you ultimately want to know potentially what's in your data. So, and that's how any of us add some context to some of the work we do. And then later this morning, we'll jump right into molecular networking. If I remember correctly from Robin's talk yesterday, less than 50% of the participants have not done molecular networking, so this is great. We'll dive into it and we'll start looking at some of the data. But first, metabolite annotation. So I'm Scott Yarmish. I'm a postdoc at Technical University of Denmark. And I am coming from a natural products background. So unlike some of the instructors here that are very heavy on the development side, I am much more on the applied side, using all of these tools in order to start taking context from the data. So first thing is, why is annotation important? So for instance, you might not have any idea what's in our data. In one case that we work with a lot of DTU, is we characterize mycotoxins in infections on fruits or other food products. So for instance, this is an image of Aspergillus niger. Yeah. This is Aspergillus niger infection on grapes, and Aspergillus niger or any of these fungi produce copious amounts of mycotoxins that are extremely dangerous for us to consume. For instance, here's an example where this study went through and they started characterizing the different mycotoxins using standards in order to do so. So they were matching based on multiple different parameters, things like accurate mass, but also retention time. In this case, this study is about 20 years old. So MS matching was not a practice that occurred here. So this is very much standard MS level 1 type of annotation. So this is an example where you will have your products and you know what you're searching for. So this is a common practice in any type of food chemistry, or you can think of it applied to any field. But for instance, this type of work that we do, we took extracts from these microbial mats that are present in the desert in Mexico. And this is what a molecular network looks like, just a handful of extracts. So we have all this data, and the question is, how do we even begin annotating this information when we have no idea what's inside? So this is very much down to the level of MS2, where we need to rely on some of these tools like GNPS to start helping us annotate the information. But the challenge is that annotation is difficult. So on the MS1 level, this is just an example pulled from a company. If you have a standard compound, you match retention time based on a standard method. You might then integrate peak area according to a calibration curve, and you can quantify your product directly. You have a mass that you're searching for, a UV signal, any of these type of characteristics can be used in order to try to hone in on your compound of interest. But really, it's mass and retention time that are integral to it. In the MS2 level, this is a mirror match from GNPS. You have to have a reference spectrum in order to start beginning to annotate anything inside of your molecular networks. But the problem is that you need reference compounds. And this is the ultimate challenge. So in the MS1 level, if you're looking for products that are readily available, amino acids or fatty acids, you can purchase them from vendors. It's very easy to set up standard profiles, and then you can start screening. But for instance, in the natural products field, it's unless you isolate enough of your compound, which we typically isolate 1 milligram of quantity, and that's used almost exclusively for biological testing. So you leave no standard reference material at the end. How in the world will you ever set up a standard method to search for your compounds? Or a synthetic route is obviously a possible means, but for natural products, these are sometimes 60-step total syntheses. So entirely impractical in order to set up standard libraries. So for compounds like that, we rely heavily on the MS2, but this is also a challenge because we need the community to deposit the spectra into the databases. So GNPS is entirely community-based, and we rely heavily on users like yourself or us to deposit data at the end of studies. That way, those databases continue to get curated. But potentially through mining of papers, we can try to pull out some of this information, but because no journals have ever required you to deposit raw MS2 data, there's practically nothing else out there to mine besides the data that we can curate ourselves. So this is why the challenge is very hard, and why in untargeted metabolomics, it's routinely quoted that 99% or around there is unannotated or not able to be annotated at the moment. And so when we're talking about annotation, there's these confidence levels that are vitally important. And these are so-called Szymanski's rules, what I've learned them to be. But there are multiple different classifications of confidence level. There are some that only have 4 levels of confidence. I think the 5 levels of confidence is much more encompassing. But this is really, I would say, your gold standard for in your paper, you say, this is the confidence level that I'm annotating my compound at. And so to quickly walk through them, we can see that level 5 is just an exact mass. So you have a feature that has a unique mass, and you say, okay, this is definitely a feature. It could be a metabolite. You don't know, could be a contaminant, but it has a unique mass away from anything else in your data. So you can say this. And then for most of our studies, we're working on accurate instruments. So you can derive a molecular formula from that feature. That gives you another level of confidence. You have an isotope pattern that you can start deriving chemical composition from. Then level 3 is where we start moving much more towards starting to piece together structures. So you might have a tentative structure, but as you might not be able to see in this example, but for instance, they say over here that they don't know where to assign, for instance, an OH group versus an NO2 group. It might be somewhere in the structure, and you have MS2 data, but there's no way to annotate it further. And then the level 2 and level 1 confidence levels really start getting quite good. So level 2, you have a lot of experimental data. You also might have NMR data coming up to this point. And you have a pretty firm idea of what the structure is, maybe not entirely sure. If you have NMR, you might have pure confidence, but you are missing a reference standard. And really that's what level 1 gets you to. Level 1 is a reference standard alongside of all the other information. If you have that, then you have the top level of confidence that you can assign in your data set. What you'll come to see is that when we use molecular networking, we're mostly working on the levels of level 3 and level 2. It entirely depends on if you have what I like to call anchor points in your molecular network. So you have a reference spectrum that some of your features might link to, and then that allows you to start piecing together what structures might be possible from these other features. So what Justin touched on a little yesterday, in order to annotate any of our data, we need databases or here I am distinguishing the difference between knowledge bases and databases. So knowledge bases, like it says here, they're largely textual, they contain information, and they sometimes have graphical information, but it's not able to be mined against. So for instance, if you search in PubChem, you can go and scroll through, you can find accurate mass information, you can find the molecular formula, and towards the bottom of the page, you might see an NMR spectrum or an MS2 spectrum, but there's no way for you to search your MS2 spectrum against PubChem's database. So PubChem and HMDB, I believe, fall pretty well into these knowledge base parameters. They're great for searching your data manually, but extremely poor for searching your data with a data-data match. On the other end, there are databases. They're numerical, so they contain MS2 information, MS1, NMR data, and they sometimes allow comparison, but not all of them do. These, for instance, good examples, GNPS and Metlin. They contain all of this data. You can mine against this data, and you can get direct matches against your data. So these annotations are much more resolute than the information-based searches. Because I can type in a mass and I might get 10,000 hits. Whereas if I put in an MS2 spectrum, I might get 10 hits, or I might get 1 hit. And then there's a bunch of databases that fall in between. I've tried to tailor these towards the biomedical community. I believe I'm right, but coming from natural product side, we don't use very many of these. So for instance, lipid maps for lipid profiling, mass bank, which was mentioned the other day. And if you're doing GCMS, NIST is, of course, the gold standard database. It has textual information, but it also allows you to do queries against MS2 or just MSMS because of EI. Yeah, so these are the available databases out there. This is what you're mining your data potentially against. Or of course, you have private databases. So many labs still have their own databases. Obviously, industrial partners have their own databases, and you're probably doing some sort of combination of these two. But it's good to know what to look out for and where some pitfalls might occur. So an example here of targeted metabolomics. So again, I've gone back to mycotoxin screening that we do a lot at DTU. This is the structure of aflatoxin B1. It's one of the most cytotoxic compounds to humans that's produced by fungi. And here, Shimadzu has created a standard package and a method in order to screen against mycotoxins. And you can see they're characterizing the different aflatoxins based on standard retention times. And here's aflatoxin B1, the same structure. And then, for instance, the application is this study here on the right. They screened different food products to see if they could detect the presence of these mycotoxin compounds. This is all done based on MS1 level data according to reference standards, so retention time matching, mass and accurate mass matching. And this is extremely robust. It works really, really well. But again, you require standards. In this case, it's targeted because they know exactly what they're searching for. So I imagine it's potentially for many of the people here in the workshop and online that you might be doing something like targeted metabolomics, where you might be searching for a product in your samples. In this case, using reference compounds is really as best as you can get. In an untargeted sense, though, I say, let's assume you have no expectations from your sample. You're going in blindly. Of course, everyone might have an expectation what you might find in your sample, but in a purely unbiased way, we might look at the data blindly. So for instance, this is the same data set from microbial mats in the desert of Mexico. And in molecular networking, I'm relying on the annotations from GNPS in order to guide me towards some products. So for instance, in this bottom right corner, we see the presence of this compound neomycin. It's a golden age antibiotic produced by Streptomyces, the big producers of our antibiotics. And molecular networking in the spectral library picks up on this compound. So I have some confidence in go in and look at the MS2 match and say, yeah, that looks great. Same thing on the left. Something unexpected that we found was this hexamethoxymethylmelamine. This is actually a coating product that's found on a lot of plastics or tires. And this is supposed to be a pristine location in the desert. But of course, we still find presence of human products in any of these water places. So I would have never expected to find anything like this. I might have expected to find neomycin, but this human-made product was an entirely unknown annotation to me, and then it popped up in the data. So this is really the power of running against the Spectrum library. And then what I'll touch on a little bit, but guys will touch on later today, is that when you have a lot of unannotated space, you can start doing things like predicting your chemical classes. So for instance, in the study we ran Sirius, and we predicted, and this molecular family here comes back as potential polyketides. And so when your annotation space is very small, you have to start trying to use some of these in silico tools to guide you towards what's present and what's not. Here is an example I like to show people of molecular networking annotation. So this is a study I ran in my PhD. And these are, this is a molecular family of siderophores. They're iron chelating compounds that all bacteria, fungi make in order to sequester iron from their environment. And the most important things to take away here is that the hexagons that are present that you can see, they're all GNPS library matched. So these annotations allowed myself, in order to start saying, okay, now I have a structural base to go from. Now can I start building more structures off of it? In this case, it's very simple because these compounds are oligomers. And so you can just kind of piecewise build them up. For peptides, this is a much easier process. Fatty acids. For more structurally complex natural products or other metabolites, this might not be feasible. So you have to be very careful with your annotations. Again, you add confidence levels to your annotations. The workflow that basically propagates from here is that you take an unknown feature. In this case, I've taken this one here, 673. I've done molecular formula prediction because it's accurate mass. I have a fragmentation pattern. And then based on this fragmentation pattern and the knowledge of the structures, I can start piecing together some of the parts of the structure. So substructure building, what we would do using NMR, but I'm doing it using mass spec. So I have some candidate core structure and maybe some extra stuff on the end that I'm not sure exactly what it looks like, but it could be either of them. And then I predict an entire structure over here. I can use a program like ChemDraw or something like this in order to fragment the compound in it, get accurate mass fragments, and then I can go back to my original fragmentation pattern and confirm if these are correct. Again, in this study, all the annotation levels were at level 2 or level 3, depending on the confidence level and how close the anchor points were to some of these features. But this is the general workflow I utilize. Again, you have to be careful what type of compounds you're annotating. For a lot of the drug-like compounds that we might observe in the data today, there are only very few potential positions that some modifications can happen, oxidation, things like this. So it's also highly possible that the smaller your structure gets, that the easier your annotations could become. But this is not a general rule. It depends on the complexity of the structure. And then how does annotation in GNPS work? So here's a screenshot. I'll just work through the screenshot for now. But when your workflow is finished, you have this, link here to view all library hits. You can select this, and then you essentially get a big drop-down menu that have all of your matches to the GNPS library. And then I wanted to just point out the things here. So for instance, this is actually the example data set for the instructors for the data set we're all working with. So it came back as this sulfa drug that's present in NIST. It's apparently in our data as well. I selected over here to view the library match, so I can see any of the green peaks down here are perfectly matched to these. This is the reference spectrum and the match perfectly to the raw data. And then importantly, over here on the right-hand side, see if I can move this out of the way. So you have these two categories. So over here, you have cosine similarity. This is the same cosine that's being used in order to create molecular families. So this is how similar your raw data spectrum is to the reference spectrum. Again, I think the threshold cutoff for this is 0.7, is an arbitrary value. You can increase it. I would not recommend decreasing it. But in this case, it's 0.98 cosine similarity, almost identical to the reference spectrum. And then you have this library quality annotation. So there are, well, there's 3 different annotation qualities in GNPS. There's really 4, but there's bronze, silver, and gold. Bronze level they could be annotated by anyone in the community. So we can go in if we find something in the data today and we can actually add it to the library. It could be instantly added as a bronze class level quality spectrum. Silver is that you have confirmed in the data and you have published it that this is present in pure form, or you can actually say in a crude extract or a cell lysate. And then gold quality is really reserved for those spectra that are being pulled from standard libraries. So anything from the NIST library could potentially be gold, but there are specific groups that have deposited reference spectra into GNPS. So there are plant metabolites, drug metabolites, and those will come back as gold quality. The most important thing I would say is it doesn't matter what quality it is. You should always be checking and making sure your mirror matches are good quality and that your spectra match up really nicely. There's also a quality that is a challenged spectrum that is like meant to say anyone in the community can annotate. You think it might be related to something, but you're not entirely sure. I honestly have not seen very many challenge spectra in the database, though. I don't know how many there are, but there is that level as well. And then to wrap up, just two more slides. So I wanted to point out, I myself do a lot of imaging work, but there is an imaging repository called Metaspace, and it is also a repository that does annotations. So you upload your MALDI data into this repository, and it searches against 4 different databases: the lipid maps, natural products atlas, human metabolome database, and it can instantly return back annotations for you. So this example on the left is a mouse brain, and it has these phospholipids present within it. I think a lot of the imaging community uses this for these purposes. For instance, on our side of natural products, we have run a co-culture where we have 2 bacteria competing, and it annotates it back as these cyclic lipopeptides that are used in competition. So this is a really useful resource for the imaging community. So I wanted to point that one out. And then the last slide is really about annotations of unknowns. So in silico approaches are really starting to become really useful for mapping that chemical space that we have no idea what's there. So the guys later this afternoon are going to talk about Sirius. In the case of the study that I mentioned a couple times, so we instantly took our different conditions, and then we were able to look at the predictions and say, in which season do we see certain classes of metabolites? Did we see any difference? And this is taking that 98% that was unannotated and start adding a little bit of context to the data so that we can maybe start finding some links. Are there certain classes of compounds that are made more in specific conditions? Or I think on Thursday, maybe tomorrow, Justin's going to talk about MS2LDA. So this is a substructure discovery tool, and in the siderophore study, so the molecular network on the left is without MS2LDA, and the highlighted nodes are nodes that I annotated or GNPS annotated. So we were able to annotate 107 nodes in that study, all as siderophores. I think 50 or 60 were new. But so then I gave it the substructures that would be present in those compounds, and I went to MS2LDA and reran it. And then I was able to come back and say, now it comes back as 351 nodes potentially have those substructures. So I've instantly tripled the amount of potential annotations that are responsible for the compound class that I want to hunt for. So these in silico approaches are super powerful to start annotating this unknown space. And that's all I have for you. I've left some time intentionally so that we had some questions. And then afterwards, we'll get into GNPS. Thank you.